Hey guys, so today we're going to talk about chapter 1. Fortunately, chapter 1 is a pretty good review of a lot of stuff that we did last year, okay? So I'm just going to jump right in. Now, be aware, okay, this is AP. We do move a little quicker. We do cover a lot of material at once. So in the event that you feel like you're getting behind or you have questions, it's really important that you reach out to me so that I can help you, okay? Make sure that you're following the schedule. Make sure that you're reading what you're supposed to be reading. Remember, Monday and Tuesday are good days to get your reading done. Make sure you watch that video on how to take notes and how to read a textbook, all right? So anyway, in a perfect world, you will have already read chapter 1. This will be me reviewing what you've already read. That's always the best way to do things. So read first, read a bit, watch some of the lecture to kind of reinforce it, read a little bit more, watch some of the lecture. You don't have to watch the lecture all at once. You don't have to take notes on it all at once. Remember, you have all week. Just stick to the schedule, okay? So this is the overview of chapter 1. Let's get started. From last year, all right, we should know that chemistry is the study of everything and how it relates to everything else, okay? It is fundamental science, all right? So we call chemistry the central science. You see chemistry in physics, you see it in medicine, you see it in biology, you see it in material science, we see it in technological advances. The way that molecules and compounds interact with each other is the main study of chemistry, all right? That's what we talked a lot about last year. We're going to go a little bit deeper into that this year and start talking about the energy and the math that we use to describe how those interactions occur. But before we get to all that, a little bit of review, right? So matter, anything that has mass takes up space, right? Remember my wonderful corny joke from last year. If you have mass and you take up space, then you matter, right? So towards the end of the year, right before we went on vacation there, the COVID vacation, we did do gases and we talked about the kinetic molecular theory. Okay, so we know that molecules are in constant motion. We'll learn more about that this year. And we know that there's a difference between the atoms and the molecules. We know that molecules can be 2 or more atoms bonded together. We know that compounds are often 2 or more types of atoms, right? So water is a compound. We would usually call oxygen gas, which is O2, right, a molecular compound. So we put that prefix in front of it to kind of indicate, hey, it's 2 of the same element, all right? A mixture has a bunch of different elements in it. You can have homogeneous mixtures. You can have heterogeneous mixtures, all right? When we talk about matter, we are thinking atoms are the building blocks of matter. They're the smallest component of a compound that retains the chemical properties of that element, okay? So every element has a unique atom. And I mean, we talked about that a lot last year. I know you guys are familiar with that, just kind of, refreshing you. On the left here, we have some ball and stick models, just some space filling models. Wow, space filling models. That's a little bit different from the normal ball and stick that we would see in a classroom. So this is a ball and stick model, right? It has the ball, has the stick as the bond. The balls are the atoms. I like space filling models for you guys because it shows you the relative sizes of the atoms. So like if we look at this kind of closely here, let me see if I got a pen selected. Oh, no, I don't. Go back. Grab my pen. Okay. We can tell that this hydrogen atom is the smallest, right? It has a very small atomic radius, especially compared to carbon, okay? So space filling models are pretty common. We'll see them a lot in AP. Now, a couple more basic things we want to review, how we classify things as far as matter. We can either look at the state of matter, so solid, liquid, gas, or plasma, and we can look at the composition of matter. So something a mixture, is it a solution, right, that kind of stuff. So let's look at those a little bit. Remember, the kinetic molecular theory kind of helps us describe the behavior of molecules in the states of matter. So In a solid, they're tightly packed, they're vibrating in place. A lot of times with solid, you'll see the word crystalline, which I think has two L's. I don't remember. With liquids, they're going to slide past each other. Okay, so if you see crystalline, we're thinking solid. If we see slide past, that's usually a pretty dead giveaway for a liquid. And energetic is a great way to describe gas particle movement. All right, they're bouncing off of each other. They're moving all over the place. Okay, so if you look up a picture of glaciers in the ocean, we can actually see all three states of water. And, you know, that's a pretty common way that we get people to differentiate between what's going on. So we can say that in the air, there's water vapor. It's a gas. It's really energetic. It's moving around really fast. Their molecules are hitting each other and bouncing off of each other. They don't stick. They have elastic collisions. Liquid water, the water molecules are held together by hydrogen bonds, right? They have intermolecular forces that are keeping them in fairly close contact, but they're not locked in place. They can slide past. And in ice, we have a rigid crystalline structure, and that's unchanging, right? So that crystal structure doesn't change. So we can see that it's, you know, the same over and over and over again, right? And I actually have a model of frozen water. Looks like this, and it forms these really nice repeating shapes. Okay, so we'll look at that some more later on. If we're classifying things based on composition of matter, there is this flow chart, which you should remember from last year. This is a year one chem chart. Okay, so you have seen it before. You saw it with me last year, or Miss Balcom if you had Miss Balcom. Kind of a yes/no flow chart, right? So, I mean, you guys can read. I'm not going to read the slide to you, so you just follow the questions, answer the question with yes or no, and it tells you where to go from there. A couple things to keep in mind. Homogeneous, the prefix homo means the same, so this means it looks the same throughout. Another word that we use for this is often solution. Okay, we'll talk a lot about solutions this year. Hetero is a prefix that means different, so this is different throughout. This is always going to end up being a mixture, okay? If we break it down even further, when we're looking at pure substances, you're either going to have an element or you're going to have a compound, okay? So just, again, I know we're reviewing. Hopefully this is review. If you have questions throughout the lecture, remember, shoot me an email, come to office hours. I'll be glad to go into a little bit more depth, all right? Now, some vocab that we need to make sure that we just have down pat. If we're talking about a substance, that's something that has a distinct property, okay? It's going to be the same each time. Its composition isn't going to, change. If I'm talking about sulfur, that substance is, it's going to be yellow. It's going to be solid at room temperature. It's going to be brittle. It's going to have a set of properties, okay? If you want to break some substances apart, you can have an element, which sulfur is a great example of an element that is a substance. You can also talk about, say, water as a compound. So water has the same molecular weight. It's, got the same melting point, boiling point. Doesn't matter what kind of, sample you've got. If it's water, it's going to have those distinct properties, okay? Remember, you can't break an element down into anything simpler while still retaining those chemical properties. So I do like to kind of put a little asterisk on this slide. You can break an element down into simpler substances. I mean, elements, right? The smallest part of an element is an atom. Okay, so we have our atom. An atom is made of quarks. And so you can break it down, but quarks, all right, these do not have those chemical properties that go with the elements, okay? Now, if we're talking about a compound, remember compounds can be broken down into simpler substances that are obviously elements. Right? Sorry, I don't know if you guys can hear that. Making an announcement. All right. Compounds, like we said, always have a definite composition. Something that we should remember from last year is the law of constant composition, or the law of definite proportions. I teach it as the law of definite proportions. but it is the same thing. So you could put a little AKA, right, also known as. Basically, what this says is if you have water, water is always going to be a 2-to-1 ratio of hydrogen to oxygen, okay? So the relative number of atoms is always going to be the same. So I can see that I have a hydrogen here, a hydrogen there, an oxygen there. Anytime I draw water, doesn't matter if I use, say, a Lewis diagram, if I use, even the Bohr model of the atom, right, where you would draw oxygen and then you would draw like its valence electrons. This is not one that we like, but no matter how you draw the thing, okay, it's always going to have a 2-to-1 ratio, right? So that is the law of constant composition or definite composition or definite proportions, rather. The other side of the classification, right? So those are our pure substances there, the compounds and the elements are the mixtures. Mixtures are, combinations of compounds or, elements, and they retain their chemical composition or properties, rather. They don't change, okay? So sometimes we call homogeneous mixtures solutions. That's the more common term for those. But heterogeneous doesn't have another word. It's just a heterogeneous mixture. Now, speaking of properties, there are physical properties and there are chemical properties. Physical properties are observed without changing the substance into something new. Very important that you can identify the difference in a physical property and a chemical property and give examples. So the boiling point, and by default also the melting point of a compound are physical properties. When you boil water, you don't change into a new chemical, right? Just because you're going from liquid water to steam, the formula for steam is still H2O. So it's still water. You haven't changed it into another substance. And remember, this word substance is what we just defined a minute ago as a set of properties, right? So it's still water. It's just water in the vapor phase, all right? So density, mass, volume, these are also physical properties. I can measure the volume of something without doing a chemical reaction. Chemical properties are only observed when you have a chemical reaction. So, when I'm changing something from substance A to substance B via a chemical reaction, that's when I can observe chemical properties. So things like flammability. If something is easily burned, well, I have to burn it to test that, right? Corrosiveness. Well, if it's sitting in the glass bottle, not doing anything, I don't know how corrosive it is. So I need to pour it on something like, I don't know, a hot dog or your hand or bologna, right? If we want to see if something's corrosive to organics, right? We use something organic and we measure that chemical property, okay? We break properties down into intensive properties and extensive properties. Intensive properties are independent of how much stuff you have. So it doesn't matter if I have a teaspoon of water or if I have all of the water on Jupiter's moon Enceladus, right, or Europa. Europa is the one that has ice. It doesn't matter if I have all the water on the moon, on Europa, or if I have a teaspoon. The density of water is 1 gram per milliliter. It doesn't change. If I want to boil all the water in a pot, all the water has to get to 100 degrees Celsius. If I want to boil all the water in the universe, the water has to get to 100 degrees Celsius. Now, the difference is extensive properties do depend on the amount of substance that's there. So when we're talking about boiling, we can intuitively know if I want to boil all the water in a pot, that's going to take less energy than if I want to boil all the water in the universe. So an extensive property is going to change based on how much stuff you have, right? More water in the pot equals more energy to boil it, okay? So mass is extensive. If I have more water, it will have greater mass. Volume is extensive. The more water I have, the more space it has to take up, right? So know the difference between an intensive property and an extensive property. When we change things, this is just kind of tied in with those physical properties. Physical changes don't change the composition of a structure or of a substance. So you have a structural change when you change state, right? We go like say solid to liquid, right? We're going to melt something. That's a physical change, just like melting point is a physical property, because we're changing the structure, all right, of the state. So this is my very structured frozen ice water, okay? But if I melt it, all these hydrogen bonds are going to, kind of start to weaken, and everything will be able to move, and they'll slide past each other, and then I'll have liquid. Temperature is a physical change. Just because I change the temperature does not mean I change what the substance is I'm looking at, all right? Chemical changes always are going to give you new substances. So if someone says like, well, we're going to combust something. Well, if you burn wood, you don't have wood left over at the end. You've changed it. So that's a chemical change. Things like oxidation, reduction, decomposition, a synthesis of a new compound, right? Double or single replacement reactions, those reactions that we learned last year. Those are examples of chemical changes, okay? Now, changes of state. Remember, if it's a state change, it's a physical change. You still have water when you go solid, liquid, gas. Hopefully you guys remember those phase change diagrams, right, from the spring. It looks something like this, all right? Where we have the solid phase, the liquid phase, and the gas phase. This is the energy, and this is the, shoot, hold on. I don't even want to get there yet. We'll get to that later. I don't want to go that far. So, got ahead of myself. Just for now, state changes, know that there is the physical change, all right, and it doesn't change the chemical composition. I want to talk about those later, those graphs. With your chemical changes, know you're making a new compound, all right? So here we're burning hydrogen and oxygen gas, we're making water, all right? When I look at this, this is a different set of characteristics than either of those two chemicals, okay? So that's a chemical change. If we want to separate a mixture, all right, a couple ways we can do it. Two we talked about last year. One we actually did, all right? We did filtration. All right, this is year one chem. Distillation, I showed you guys, we talked about. If you don't remember, distillation we talked about, that's where the word a still comes from, right? So if you find a still out in the mountains, they're making moonshine, you're distilling things. So both of these we talk about in year one. We're going to review them. We're also going to talk about chromatography, okay? And our first lab, the first lab I do in chemistry, in AP Chem, is actually a chromatography lab. And we're going to kind of play that by ear for this year. I don't know exactly how we're going to do it virtually. I think I will do it and film it and show you guys and that kind of thing. But if we do come back face to face, we will actually end up doing a lot of labs in a row. We'll have like weeks of just lab. So I'm kind of playing that by ear. I'm not sure yet. But let's just take a look at some of these. Filtration. You separate a solid from a liquid, right? You're pulling it out of usually a heterogeneous mixture, sometimes out of a solution, but most often a heterogeneous mixture. This is how you make coffee, right? You dump the coffee grounds in the coffee filter, water runs on top of the coffee grounds, it goes through the coffee filter, filters out the coffee grounds, and you just get the coffee itself that ends up in your beaker, right? This is a distillation setup, all right? Now, this setup moves from left to right as far as like time is concerned. So you are heating this mixture, right, this solution. The water, right, boils way before salt boils, right? So when you're using distillation, you're using differences in the boiling points, all right, of substances. Okay, that's what distillation does. So the salt is not going to boil. You're talking about turning solid salt into a gas, right? But the water is. So the water boils, and then in this middle part, you actually have water that's running constantly. Right? So this is running water. And there's a tube within a tube in this distillation column, right? That's what that thing is called right there. It's called a distillation column. And that cold water from the sink cools the glass down, and it condenses this boiling water, and gravity then pulls it downhill and condenses, and it ends up in our flask. Now, the salt, because it hasn't boiled, stays behind. And so over here, I end up getting nice, pure, fresh water, and this becomes an increasingly concentrated solution of salt water. Eventually, I will have nothing but salt left in the flask, and all the water will be boiled over to the other side. Chromatography is something new, we haven't talked about. There's a lot of different ways to do chromatography. And normally what we're doing is we're separating things, right, based on their ability to adhere to some surface. So if we look at these, and we actually have some of these here in the classroom. If we look at these tubes, okay, you have your solvent up top, and as gravity pulls things down, all right, they will separate out. You can see like here is, time equals 0, right? This is our start. Say time equals, 10 minutes. And at time equals 30 minutes, all right, we're starting to get these bands, okay? And they're separating out, all right, based on molecular size or their ability to stick or adhere to whatever it is we've got in here. This can be a resin, like this stuff right here. This can be a resin, it can be wool, it can be glass beads, it depends on what you're trying to separate. Our first lab is thin line chromatography. We're going to use paper to do it, and it's similar to this. And we actually will use a stain as well in order to get everything to show up. But we will talk about in a different video some more details on thin line chromatography and RF values and some things like that. But by looking at how far these clusters move, we can tell a lot about what kind of molecules are in our solvent. Now, let's switch gears one more time. Right? I know chapter 1 covers a lot of stuff. So if you need to pause the video, remember, you can pause the video. You can take a break. You can always come back. But assuming you want to continue on, we spent a lot of time in year 1 talking about numbers, okay? We're going to talk about a lot more numbers this year. Things that we should have fresh in our head, things that we should review if we need to. The units of measurement that we use, the quantities that we measure and calculate, right? How we indicate uncertainty in our measurement, our percent error calculations, okay? Our sig figs, right? Which decimal is the guess, all that good stuff. And then finally, how to do dimensional analysis, right? How to do our brackets. So let's look at some of those things. First, we use the SI unit, all right, in order to do every calculation here in AP Chem. We have a different base unit based on what you're measuring. So if you're measuring mass, we're going to use the kilogram as the base unit. If it's length, we're using the meter. If we're doing, how much substance we have, we use the mole, right? So make sure you re-familiarize yourself with all of our little abbreviations, okay? There will be more to come. Remember that Kelvin is the SI unit for temperature, all right? That's important. We use Celsius to record things, but we can often convert to Kelvin to do our calculations, all right? Remember your prefixes. You don't need to memorize this whole table, all right? However, a couple new ones that you're going to see in here. Pico, nano, micro. This little symbol here is a Greek letter mu. It looks like a U with a tail on the front. We will talk about femto a little bit, but micro, nano, and pico will be something that you see in this class. We don't really get into the bigger units above kilo or kilo, but just be aware that there are some. Okay, so like you may have seen terabytes in computer storage, right? So that's something that's 10 to the 12th, right? Is our conversion there. So just refamiliarize yourself with these. These are the big ones right here. Okay, these are the big guys. Big ones, we'll say to know. All right. When we talk about mass, okay, I'm just going to kind of run through this. Remember, we use the kilogram as the base unit for the SI system, right? This is important. SI uses the kilogram. The metric system uses the gram. They're not exactly the same thing. Right? We usually use them interchangeably, but that is one difference there. For length, we use the meter. For volume, it is a derived unit, so it's not a base unit. We use the liter or the milliliter in chemistry because we're usually using micro scale. Right? Remember that a liter is a cube that's 1 decimeter on each side. So remember, a decimeter is a tenth of a meter, so 10 centimeters. So 10 times 10 times 10 is 1,000. 1,000 centimeters cubed, because centimeter times centimeter times centimeter is a liter. So some things that we want to make sure that we know here, 1,000 cubic centimeters equals 1 liter, okay, which is the same thing as remember that 1 centimeter cubed is the same thing as a milliliter, all right? Keep those things kind of fresh, right? And remember, if our units don't cancel, all right, we got to have exponents, right? And that's something we'll see quite a bit in this class. We'll talk about temperature. Remember, temperature just measures hotness, all right? Is something hotter than something else, because heat always flows from hot down to cold. So I know that after we left, we did specific heat. Some people chose to continue working, some did not. If you did not work on in the spring on the stuff with specific heat, I'm going to post a little bit of review stuff when we get to that in AP, but it would be smart to go back and look at the notes that I posted from the spring if you're still in those Google Classrooms. So specific heat and the flow of heat is something that we start, you do like an introduction in the first year, and then we get a lot more in depth here in AP. Couple things to keep in mind. Celsius is what we measure on our thermometer. Kelvin is what we convert to. Kelvin is the base SI unit for temperature. Right? Celsius is based on water, where 0 is the freezing point, 100 is the boiling point. So Celsius can have negative values, right? If you're below the freezing point, you're negative on the Celsius scale. Kelvin doesn't have that. The lowest possible temperature in Kelvin is absolute 0. It's 0 Kelvin. We'll spend some time talking about that very soon, okay? But just know the difference between Kelvin and Celsius. Also make sure that you can convert Kelvin to Celsius. Wow, that is really complicated to say. All right, with Fahrenheit, we don't use it in here. I'm not going to make you memorize how to convert it because we don't use it. But if you want to know how, there are the formulas. Density is something else that we derive. It's mass divided by volume. A lot of people in the entry diagnostic had some trouble solving this for volume. So remember, if D equals M over V, and I want to find what volume equals, I multiply volume to both sides. That tells me that M equals V times D. So then if I divide by density, that tells me that volume equals mass over density. Okay. If you're comfortable with algebra, all right, another way that you can do that is to say, all right, if density equals mass over volume, and I know when I solve for a variable, I need to have it on top, all right, then I can say that 1 over density equals volume over mass, right? I can take the reciprocal, and now I just need to multiply both sides by M. So M over D equals volume, all right? I don't care how you solve it. Just make sure that you're up to date on your algebra rules, okay? Some numbers that we're going to look at. Remember the difference between a counting number or an exact number and a measured number, okay? If you have 12 eggs, you have 12 eggs, you don't have 12.001. Remember, counting numbers are perfectly exact. They're infinitely significant. Measured numbers, though, we have to determine that last digit, all right? So there's some uncertainty in our measurements. Every single measurement has uncertainty. It's always the last digit in the measurement that is our guess, okay? And when we get to sig figs here in a minute, remember that's, what we're looking for. How many sig figs does a number have? And that should tell us intuitively how accurate the measuring tool is. When we talk about measurements, remember the difference between accuracy and precision. Accuracy is close to the actual correct answer. Precision just means the measurements are close together to each other. So think about our dartboard. You can't be accurate if you don't have good precision. If you're accurate, you must be precise as well. You can have good precision, right? The second one, all of our darts have landed up here, but we're way off the mark. So we're precise but not accurate. And if our measurements are all over the place, then we're not precise or accurate. Remember, sig figs tell us how to round things, okay? We don't want to overstate the accuracy of our calculations, okay? When you do an experiment, when you report that data, your experiment is only as good as your worst, least accurate measurement. So we have to make sure that if we're doing calculations, that shows up. We should be able to look at a number and say that's significant, or sorry, we should say that's very accurate. We should say that's not very accurate, right? So if I tell you that you need 12.1 milliliters of H2O, well, you know that your graduated cylinder just needs to have marks like this, all right? Because the last digit is the guess, so that tells me that this digit, there's nothing in between those marks. On the other hand, if I tell you you need to have 12.01, well, now my graduate, like milliliters, now my graduated cylinder needs to have a mark for 10, and then 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 11, right? It has to have all these little tick marks. So this is now the guess, all right? Whatever your last digit is, you have to have tick marks must be present, right? A tick mark must be present on your instrument. The more tick marks you have, the more expensive the measuring tool is, but also the more accurate it is. Okay, same thing with like, mass or something. We don't want to have calculator diarrhea, right? We don't want to have like all these numbers listed out. So make sure that if we're reporting numbers, we use sig figs. If we're calculating sig figs and you need your zero rules, remember, non-zero digits are always significant. So the numbers 1 through 9. If you have the sandwich rule, right, zeros between sig figs. So something like 101 has 3 sig figs, right? That's non-zeros are always significant, and that zero is sandwiched between the two. So I have 3 sig figs here. Okay. Zeros at the beginning of the number are never significant. This is called the leading zero rule. It doesn't matter if I write that or that. It's the same thing. So these zeros, right, they don't count. They're not significant. If you have zeros at the end of the number after a decimal, then they are significant. So there is a difference between this and this. Right? That is significant. This has 3 sig figs, all right, and this only has 1. This is significant. If you have trailing zeros that don't have a decimal, all right, these do not count. So this only has 1 sig fig. Okay. If you had 1,000 with a decimal, all right, now they all count. This would have 4 sig figs. Remember, if you just see a decimal with nothing exact or nothing accurate, you read it as exactly, right? So this is 1,000. This is 1,000 exactly, right? Or exactly 1,000. When you add or subtract, remember we're looking for the fewest number of digits after the decimal place. So if I did something like, 2.2 plus 2.22, all right, I only have 1 sig fig, 1 digit after the decimal place. So I do my math, and now I'm going to look right here and I'm round based on that 2. The 2 does not round me up, so I would say my answer is 4.4. If I multiply or divide, I'm looking for the least number of sig figs in the calculation. So if I have 2.2 times 2.24, this has 2 sig figs, that has 3 sig figs. So whatever my answer ends up being, I need to round at 2 sig figs. Okay, so that's the difference. When we do dimensional analysis, last slide, right? I promise. When we do dimensional analysis, remember we're using our brackets to convert, starting given unit 1 to some unit requested, right? And we use conversion factors in order to do that. So if I say, we're going to convert, let's do something easy. Let's say 1,000 milligrams, and I want to convert it to, let's say, kilograms. I write my given, 1,000 grams. Gram unit goes on the bottom. Okay, milligrams. Oops. Okay, prefix always goes to the base unit. You write it right. Remember, we're dividing out units. So 1 gram has 1,000 milligrams in it, and there are 1,000 grams in 1 kilogram. So milligrams on top and bottom, it cancels. Grams on top and bottom, it cancels. I'm left with kilograms. That's what the problem asks for. 1,000 divided by 1,000 is 1. 1 divided by 1,000 is 1/1,000th of a kilogram. And that would be my answer. Okay, remember, box in your answers. Don't forget your units, right? No naked numbers, right? So that is a review of the first chapter. Hopefully you've already read it. You do need to read it, okay? Every week, follow the schedule, read what it says to read. Watch the video in chunks, all right? Read a section, watch the video about that section, right? I've built these PowerPoints to go in order with the chapters for the most part. So read your section, watch your video, reinforce it, okay? If you have questions, shoot me an email. Let me know. All right, let me bump out of this and stop presenting. So if you have questions, let me know. Shoot me an email. I'll be glad to help you out. Stay on top of the schedule, all right? That is the most important thing. I am going to post some more videos this week, so get ready for them as we also, kind of supplement our material. So I'll see you guys in those videos.